analogy, so if we have two conductors serving as a capacitor, of course, we always need to evaluate the geometry, and we have to choose a good coordinate system to work with. Okay, first step. Then, we can just assume positive charge of Q and negative charge of Q are deposited over on the two conductors, respectively. We need to maintain charge neutrality. Okay? Charge needs to be neutral. Okay? So once we assume there are charges over the conductors, we can calculate the resulting E-field intensity distribution. Okay? Gauss's law is probably most appealing, but if you cannot do it, you can just use Coulomb's law. And once we know the E-field intensity, we perform the negative line integration to find the potential difference between the higher end to the lower end. Okay? So once we have this potential difference, we can just put it in the denominator and we put Q in the numerator, and therefore we have the derived capacitance. Okay? So the procedure is to assume charge Q and negative Q being deposited over the two ends, and then you calculate the E field, you calculate the potential difference, and then you take the ratio of the charge and the potential difference. Okay? First case we're going to analyze is the two parallel plate capacitor. Okay? In these derivations, the assumptions are always made to assume these two plates are very big. What does that mean? It's true. I mean, if the two plates are not really big, then you don't have an easy answer. But I want you to tell me, what does that mean? I mean, physically, if you have two very big plates, this is something you learned. And your second examination is coming up quickly, so you better review. If you have two big metallic plates, you deposit charges onto it, you have positive charge and you have negative charge, it will generate constant E-field patterns. So the E-fields are actually constant. It is not position dependent. Okay? So why do we have to assume that plates are very big? If the plates are not very big, at the edge, right? Assume you have a positive charge and you have a negative charge. At the edge, field start from the positive charge and ends up at the negative charge. So at the edge, your E-field intensity would definitely not be a constant. You will be spatially dependent. Okay? So in all textbooks, we only analyze somewhere in the middle, where you have very uniform and constant E-fields. At the edge, we usually don't talk about it. So that's why in almost all the textbooks, we have to assume the plates are very big. But in reality, we can also say if the separation between the two plates is very small, then the plates are effectively very big. Okay? So we're safe. Alright, so if we deposit charge Q on the top and negative Q on the bottom, and we know the plate surface area, so we know the surface charge density is Q divided by S. So we assume that we deposited those charges. And in the previous case, we already know that the E fields, in this case, is pointing downwards, right? Fields emit from the positive charge and ends up at the negative charge. So the direction is in the negative Y direction. And the amplitude is rho divided by epsilon. This is something we derived already, right? So once we know the E field intensity, all we have to do is perform line integration and remember this negative sign. Okay? So the potential difference between the bottom plate and the top plate is Q times D divided by epsilon and divided by the surface area. This is something we learned already. I bet each and every one of us learned this or memorized research result starting from high school, right? So if you have metallic parallel plates, the capacitance is determined by the dielectric material you use and the surface area and its separation. So again, such a simple relationship, you have to know which one is giving you the material dependence and which one of the parameters are telling you the geometric dependence. Epsilon is definitely material dependent, right? And these two together, the ratio of surface area to the separation is geometry. Okay? So as an engineer, whenever you look at your result, you have to teach yourselves. If you want to change or you want to tune certain value, what to tune. For example, if you have two parallel plates and your first job, after your graduation, your very first job is to make a capacitor with a very high capacitance. But your geometry is limited, right? To have two parallel plates. You want to increase your capacitance. How would you approach it? You remember 3 years ago, the professor taught you such a simple relation, right? You dig out your class note, you look at this relation, epsilon s and divided by d. You want to increase it. So what is the most effective way to increase the capacitance value? If you are limited to the parallel plate geometry. The question might be intriguing, might be misleading. Would you choose to start with epsilon to have different material? Because you think, well, my boss is telling me I have to make parallel plate capacitors, so these two are the geometric dependence, right? I have to fix it, so I have to change material. But if you look up in the tables, epsilon cannot change a lot. Vacuum is 1 times epsilon 0. Silicon, maybe 12. It's probably the best, even not. So you can only increase it by a factor of 12. Okay. So tell me, what is the most effective way to increase the capacitance value? Well, epsilon is definitely not the best way to go because you're limited by materials in nature. Okay? So in this case, even though your geometry is limited to the parallel plate scenario, you can either increase the surface area or decrease the separation. So which one is more effective? DA. Increase the surface area or decrease the separation? Yeah, decrease the separation. Why? Because you are an engineer and you're working for a company and your boss wants to save money, right? If you make the surface area very big, your final product will be big, right? And you're using more metal, which costs more and takes more space. So the most effective way is to shrink the device dimension. Okay? So that's the very first lesson for engineers. You have to take into consideration efficiency, which includes money. Okay? All right, second example. Now we have two conductors. This is something we analyzed in the very last page of the previous PowerPoint set. This is a coaxial cable, right? I have the center conductor, I have the outer ground conductor. In this case, these two conductors are again filled with a dielectric. So this is actually like the transmission line that we analyzed. This is exactly the transmission line that we analyzed in the very first chapter. But now we have sufficient knowledge to derive its capacitance value. Okay? How to do that? Well, again, we can assume, we don't have to assume because this is such a well-known case. We already know its field value, right? Of course, well, given the length is L, I deposit charge Q onto the central conductor and negative Q onto the outer conductor. I know that all the field lines are in the radial direction. Again, I'm working in the cylindrical coordinate system. So I'm using this lowercase r to denote the radial direction. So this is using Gauss's law, right? 2 pi r. 2 pi r is the circumference of the circle times L, that is the surface area in the radial direction. I enclosed charge of Q, but now I'm inside this dielectric, so this epsilon is really the absolute permittivity. Okay? I integrate that to find the potential difference. So that's my potential difference. Okay? Now, Q divided by the potential difference gives me the resulting capacitance. Again, I want to train you properly. Look at the expression and tell me where is the material response. The material response is capped inside this epsilon. All the rest are the geometrical response. Okay? So if you still remember, in the previous case, we saw this 4 pi b, right? 4 pi b, 4 pi something represents a spherical geometry. And now you have cylindrical geometry, you have 2 pi something. Why? It's due to the fact that your surface is related to the circumference of your circle. It's 2 pi r. Okay? So probably in the future, whenever you see the capacitance having 2 pi dependence, you can guess its geometry is more like cylindrical. And 4 pi something is more spherical. Okay? Now, you should be very proud of yourselves. Why? Well, if you still remember, do you still remember this table? This is something I showed you, right? For transmission lines of different geometries. I showed you each transmission line has its own resistance per unit length, inductance, admittance, conductance, and capacitance, right? Take a good look. This one is the parallel plate. Having two parallel plates is actually a transmission line. And we just analyzed that resulting capacitance. It appears differently because here is per unit length. Okay? So in this case, the coaxial cable, 2 pi epsilon divided by natural log B divided by A. It's just taking this length out. So you have the capacitance per unit length. Okay? So you should be very proud of yourselves because starting from the semester, you were forced to take the concepts of a transmission line being comprised of lumped element circuits. All these components, you just use a symbol, right? R prime, L prime, G prime, C prime, but you don't really know how to formulate all these parameters. But now, gradually, you are capable of deriving the C prime for coaxial cable and the C prime for parallel plate transmission line. You have improved a lot, right? You should be very happy. Give yourself some applause. Okay. Okay, the danger is, well, the danger is the thing that the professor does not teach would appear in what? Exams. It's very difficult. Okay, so if you have two wires, two parallel wires, it also functions like a transmission line. So probably I'll try my best to help you. So either include it in the homework or it will appear in your examination. Okay? So some student might be very happy and excited. Now you can derive 2. So together you have 12. So we only knocked down 2. So we have a long semester to go, right? But eventually, all these can be deduced by yourselves. And that's what I call improvement, right? So now do you see the purpose of teaching you transmission line in the very first place? I give you the entire picture, and then we spend the entire rest of the semester to fill the gap. So you feel your improvement every day.